Robotik in der Industrie. Der Podcast mit Helmut Schmidt und Robert Weber. Hello everybody and welcome to a new episode of our Robotics podcast. My name is Robert Weber and I'm sitting again in Freising next to Kristen and to Thomas, and we want to talk in this episode about the whole topic of motor control, sensing and power stage, and I'm really looking forward to this discussion. But before we start, Thomas, please introduce yourself briefly to the listeners.
Yeah, hello everybody. Thank you, Robert. My name is Thomas Schneider. I'm systems engineer for industrial systems, focusing on robotic applications, working for TI now for 22 years. Yeah, thank you.
And Kristen.
Yeah, my name is Kristen Mogensen. I'm working in the same team as Thomas, focusing on robotics. Here also I've been working at TI for 18 years.
So we have some interesting topics today. Motor control is one topic, sensing is another, and power stage. How are these three topics played together in the robot, Kristen?
Okay, so when you look at the robot, right, you have to think of the movement of the robot is always based on the motor. The motor has a mechanical piece of it where you need to have a typically brushless motor, so a three-phase motor with magnets inside. It's the typical approach today. This motor typically gives you the best torque performance. So the torque you need to actually do the actual movement, and you can move enough weight, right? And then you need the electronics to actually move the motor, which is the more interesting part for TI, of course. Sure. Now, with that piece, you have a small subsystem you need to implement. That small subsystem, you need to have a real-time communication to the robot controller so you can talk with it. You need to have a real-time processor which has specific hardware features or hardware sync features in the peripherals that you can measure and control the motor control in the right time, in the right windows, in the right time sync. Because you can imagine if you, let's say, start controlling the motor, but the angle sensor is not in sync with the signal you give to the motor in the right way, you're basically introducing losses to the system because it's inefficient, because you're always trying to regulate to something that's not what the real state is. And this is what we have specialized with the TI processors now for the last, I would say, 25 years or longer, with first the C2000 family, but also now the AM26 family and also the AM24 family, that we have very tight peripheral connections for the right features to do a very time-sensitive motor control in a very deterministic way.
Mm-hmm. Thomas, you want to add something when it comes to sensing. So how do you combine those three topics then?
Yeah, actually for the precise movement of the robotic arm, or also for a mobile robot, or for the locomotion of humanoid robot, these three systems need to play together in real time. So the control loop needs the information from the sensing portion in real time to control the currents for the motor. And here our real-time microcontrollers, actually with the corresponding interfaces to the encoders and also between the different motors, are crucial to achieve those real-time communication.
Do we underestimate these topics a bit when it comes to the certain discussion we see in the whole field of robotics? We talk a little bit about AI, robotics, world models, and nobody talks about hardware in the moment.
I think it is a little bit ignored, a lot of it, when you go in the whole discussion with the simulation models, mm-hmm. right? You simulate that the motor is moving in a specific way, in a specific speed, with a specific dynamic performance. And then you just assume this motor drive can do it. And this is something where actually you need to verify this can be done. And a second piece, which is an even more crucial piece, is the motor control gets hot. Mm-hmm. And you can think of it, if you take a humanoid, the surface, or any robot that's close to a person, right? The surface of that robot is not allowed to be more than 42 degrees. Mm-hmm. Because then you can touch it without it feeling hot. Mm-hmm. If it turns up to something like 54 degrees, if you touch it for 3 seconds, you get a 3-degree burn. Mm-hmm. That's a big issue. And this is why the efficiency of those systems are super, super critical. The second problem is...
But how we can go further with the systems?
So the second issue is the size, right? So you have two things where you have a very small size and you need to get the thermal away. Mm-hmm. And this is where it starts to get super, super tricky, and also where we see customers saying, well, standard MOSFETs, yes, you can kind of make it work, but going for GaN FETs actually gives you a little bit boost on efficiency, and it starts to be worthwhile, this price versus feature option. So we see a trend moving more and more to GaN FETs, simply because you can achieve that a little bit higher efficiency because of the function of the GaN FETs. And also because of that higher efficiency, also the losses on the system get smaller, so you can build a smaller design. So it's kind of all coming together. The same is also with the processors, right? The processors are starting to get smaller and smaller in package. And this, of course, is enabled because the nanometer process is getting smaller and smaller. So kind of all these small things are coming together in a way where you can say, I can minimize my system, that everything starts to fit together. But this comes back to this discussion from before where I mentioned the processor, the communication to the main controller. As Thomas mentioned before, you have the encoder interface. Second thing here with the encoder interface, it's not just one interface. It can be 2 or 3, because you need, if you have a gear, you have to have the encoder angle on both sides. If you have functional safety, potentially you want a third one. There's many small things you need to think of when you do that system. For the current sensing, it's a similar discussion. I think we get back to it a little bit more in detail, but the current sensing, you also need to have the right peripherals in the processor to get the right data from the current amplifiers. And all of this comes together, and this is where we also try from TI to try and show how can we make the smallest system and still give you the performance you need.
Yeah, especially with the new type of robots, the cobots, where you have now a decentralized architecture very often. I mean, in the past, for the heavy load robots, you had a centralized architecture to get rid of the heat because of the high power consumption. It's difficult to get the heat away inside the joint of the robot. But with the smaller type of robots, customers are moving more and more to a decentralized architecture, having the complete motor control inside the joint. And here it's really important that you get rid of the heat and also have high efficiency. And here the GaN technology, for example, with the high efficiency is a good solution from TI for cobots and the decentralized architecture. Also the microcontrollers with the smaller sizes now, they are getting smaller and smaller that you can directly put them inside the joint. So that's also something what is getting more important for the cobot type of robots. And also here then you have the industrial communication because it's a decentralized architecture. So you need kind of real-time communication to synchronize the motors. And that really needs to happen in real time with low jitter, low latency. And the peripherals here in the processors and microcontrollers, like with the ICSS subsystem, the industrial communication subsystem in the Citara process, for example, where you have the flexibility to implement the different protocols like EtherCAT, Profinet, and so on. So you're very open here for your protocols. Also on the encoder side, you have the communication of the encoders in the joint now. So, and here the processors are also supporting the different type of encoder protocols like BIS, NDAT, Hyperphase, also Hyperphase DSL safety, the safety protocols if you want to have a safety encoder. And that's something here where customers can be really flexible.
Before we talk about current sensing, I want to come back to motor. What are the typical motor types seen in robots? What do you see in the market?
So today now it's the BLDC motor, and I like to define it also as the BLDC motor, but a sinusoidally wound motor. So basically you do field-oriented control with it. We have seen some use of brushed motors in the hands because of the low power in the hands. However, what we also hear is this is also moving to the BLDC motor because the brush motors, for instance, create so much, let's say, dirt that you cannot use them in clean rooms, for instance. So you limit the way you can use your robot because of this. And there we see a clear movement. Everyone is moving to these.
But do you see an improvement? Do you see new trends, new ideas coming from the motor side?
I would say right now we see a wish to try and figure out how can I do the motor control without magnets. But this is still very experimental, and let's say there isn't a clear solution on the market, and it's also something we see is not really being used in the production-ready robots. However, there is a clear wish, and this is a clear trend of saying, I want to try and fix my supply chain, and magnets are difficult. So if I can avoid magnet, my life is easy. super. But
sure.
it's a discussion we see customers are trying to solve now, or trying to at least very high-level research-wise trying to figure out, is there other options, because I want to get rid of this dependency.
How does it influence you as TI when we have discussions in a market like this?
So this discussion actually from a processor perspective, if you look at the algorithm, is very similar. So from a chip perspective, they have enough horsepower to do it now. That was the problem in the past with a lot of these motor types. They needed more algorithm power to actually do the math around it. And this is starting to be possible now. So it's one of those where the ideas existed already 50 years ago, but it hasn't been possible
15 or 50?
50.
50, yeah.
So all these theories, they existed for a long time. It's more a matter of, yes, you knew roughly how to do it, but it was not possible to do it in an economically feasible way. Mm-hmm. There are some systems already using these type of motors today. I think one of the... Yeah, I can probably not mention that customer name,
no.
but there are actually solutions on the market today using this type of motors, but not for robots, but in other systems.
Sure. And when it comes to current sensing, because Kristen already mentioned current sensing, what type of current sensing is needed for the drive, and what is TI's perspective there, or USP?
I mean, TI offers different options how you can do the current sensing. I mean, we have ADCs and we have delta sigma modulators. So in our MCUs, specifically the real-time ones like the C2000 or also the Citara devices, they have already integrated ADCs to measure the current with ADCs and also to synchronize the current measurements, because it needs to be synchronized to your PWM signals and so when you do the current measurements. On the other side, we are also offering delta sigma modulators so that you have also the option to do measurements with these kind of current sensing. And here we also have peripherals integrated for the sync filter, for example, in the Citara devices. That's done in hardware, so to offload the CPU here. These are the different options depending on your accuracy and where you do the current measurement, which type of current measurements you're doing, shunt-based or Hall sensor-based, and the bandwidth and ENOPS, the accuracy, what you need. So the customer has the choice here, which type of measurements he wants to do.
When it comes to sensing, when it comes to sensing data, etc., AI can play a crucial role in this whole application, or am I wrong?
I would say here, yes, AI can play a crucial role. There is a lot where you can start trying to estimate and get a better current measurement using AI to better understand the current movement. Because at the end of the day, when you do sinusoidal control, you also have a sinusoidal current in the system. So you have a rough idea where you're supposed to be. And you can also model this very nicely. Using those AI functions can also, for instance, help you do torque measurements based on the current because of the math around the motor control. With the current, you can actually calculate a lot of these additional information using AI, which can help you better understand and diagnose your system. So yes, there is a lot of that.
Is it your aim to go in this direction, or is it more the aim of the robotics companies? Because I see different strategies there. So some robotics companies say, we want to do that. This is our part because we have a value-added service or value-added AI to our product. Or is it your turf?
At the end of the day, it's a split, right? Because if the processor doesn't allow enough processing power to do it, or the right accelerators, and this is where TI, we are focusing a lot on the tiny AI accelerator, which we put into a lot of these real-time cores, and they are already on the market today with these engines. So we already have customers doing, for instance, arc detection for solar inverters. Or you can use the current measurements to measure if the bearing of the motor is starting to break. We have already these engines and an example showing how to do this. So
we are offering the hardware for it, and we offer the tools for it to train your models, but we will not collect the data from the motor and train the models and provide this into our
So you
microcontroller.
provide the infrastructure.
We provide the infrastructure, the SDK, the Edge AI AI Studio, for example.
Where we already mentioned that
yeah,
in the first
exactly.
episode. Yeah.
And then the hardware accelerators, like in the C2000 devices, the neural network processing unit to offload the main CPU on the higher performance processors. We have also the DSPs and the matrix multiplication accelerators in hardware in it. And for these hardware accelerators, we offer the SDKs and how to use them. But at the end, the data collection, the trainings of the model and so on, the model selection, that all has to be done from the customer. And especially then for the use cases for predictive maintenance, I think that's coming more and more where AI is used.
Yeah. We talk since 15 years about predictive maintenance. We are not yet there, right?
No, I don't think
Still not yet there.
Yeah. Now we have the tools.
We have the tools.
We can collect the data. We can simulate and test it.
Kristen, you want
I think one thing here is also important to understand with the discussion, right? We as TI, we build electronics, right? We don't build mechanical hardware. And this is where we also do a lot of the collaboration. We help customers build these electronic systems with our components, and they bring the hardware. And then we learn together how to use the electronic in the best way for the hardware. Yeah. And this is a key thing also with the whole doing the diagnostics and all these things, right? It is you need actual the mechanical, let's say, solution to actually get the right data. And this is where we try and collaborate as much as possible. Of course, there are companies that want to do more than others, but at the end of the day, we try and give the guidance of how to use the TI part with all the tooling Thomas mentioned before, right? How can you use it to make a smart system? And this is what we try and show and also what we try and help customers with.
So coming back to hardware, because we talked a little bit about AI and machine learning, you already mentioned the communication layers or the communication protocols you are using in the robot. Can you please explain once again how does the drive communicate with the robot controller at the end? Thomas, you want to start?
Yeah, it depends on the architecture. Yeah. I mean, if you have a centralized architecture or a decentralized architecture, in the centralized architecture, the distances are quite short. And here you have often also proprietary solutions. When it goes then over longer distances to the arm of the robot, like in cobots to the joints, then there is for the communication and the control, you have the industrial Ethernet communication protocols like EtherCAT, for example. And on the other side, from the encoders, getting back the position information, you have the encoder protocols like NDAT. And typically then those encoder cables go to the base of the robotic arm. And from there, they are aggregated together. And from there, it goes then via EtherCAT back to the robot controller or to the cabinet, that you don't have all the cabling from the 6 or 9 joints, whatever, how many axes you have, to route to the robot cabinet. So saving cabling going then from the base of the robot via EtherCAT or other Ethernet-based protocols.
You want to add something, Kristen?
Yeah, and also it depends on how the robot manufacturer built their software architecture, right? Because at the end of the day, to do the robot movement, you need position control. Mm-hmm. But to do position control, you need to do speed control. And then you need to do current control. And depending what the customer says the drive is supposed to do, is it only doing current? Is it only doing speed? And where does the precision lie? Mm-hmm. Depending where you place these blocks in the either robot controller or in the drive, it depends how fast do you need to communicate and how much data do you need to communicate. And this is also this with the recurring and also using the real-time protocols for this, right? That's why you need the industrial real-time protocols to be able to communicate reoccurringly fast enough to choose where do you want to put your control. What we typically see is you do speed control and current in the drive, and then you put the position in the main MCU, which also kind of makes sense because the position control, you need to align all motors with each other to get the right smooth movement, right? The main controller needs to know all the data anyway. So it makes sense that it also does the math for it. Mm-hmm. And then you can offload the MCUs. But at the end of the day, it's a customer choice. There is no right or wrong, right? It's a choice, and there are reasons for doing in one or the other way.
And not only the robot controller, but also the safety module needs to know the position of the joints. Exactly. And here it depends then on the architecture, how you route the cabling or your communication protocol, because the main controller needs it in real time, but also the safety module needs it kind of in real time to be able to react fast enough in case of something goes wrong.
Mm-hmm. I want to come back because our episode is about motor, current sensing, and power stage. What kind of trends do you see when it comes to power stage?
So if you look at the power stage, what we see as a trend is definitely for cobot, humanoid, it's much talking about miniaturization and high efficiency and using the technologies to achieve the highest efficiency. Of course, there is
but that was always the goal, right?
Yes, but with the humanoid, it's gotten more extreme on how small it needs to be.
Exactly.
There is a second goal that's starting to also appear in these discussions. It's also, if I want to mass produce it, how much is it allowed to cost, right? And this is exactly where, for instance, technology like GaN FETs, they are in a price range where they're starting to be interesting, but still maybe a little bit expensive. But what we also see with GaN FETs, the more they get produced, the cheaper they will get, and eventually they will be so cheap, it's not a question anymore. The additional benefit they bring you is worth it because they are very similar pricing with the MOSFETs. So here we definitely see a trend of customers testing more and more GaN FETs because they see the benefits they bring, but they also see the prices going so much down that also commercially it makes sense. And then it's not a question anymore. The GaN FETs basically bring one caveat to it, very fast slew rates, switching times. And this you need to also compensate when you need to ensure that your current sensing is not affected by these high slew rates. And this is where we have done some analysis from TI with our different current sense technologies. So trying Hall-based, trying shunt-based measurements with delta sigma modulators, with high VIN input or high common mode amplifiers, and trying to compare and see where does what fit in the best way. That being said, right, we discussed a lot here. This is all low voltage, I would say 60 volt, probably up to 100 volt type systems. We also provide gate drivers with basic and reinforced isolations for the standard robots. Here, the discussion is more a price of I need to cost optimize and make the system more affordable simply because the market is mature. You roughly know what you need to do, but you need to architect a system that is still commercially sound. And this was not a discussion or an issue in the past. So a lot of times, some of the solutions we see today, they are over-designed because you got the price you got, right? And this is not the case anymore. There is a price competition now, and the functions are very similar on the robots, right?
Yeah, another trend I think is the regenerative braking. So in the past you had your braking resistor.
Does that make really sense? So the discussion is it really makes sense?
Yeah, I mean, you want to save the energy what you would
But there
burn.
were tests, I think I was 10 years ago, they tried to do that, but they said, oh, it doesn't pay out at the end. And is it now in this stage that they want to do that really in big scale?
So if you look at the mobile robots, they already do it today because the mobile robot are carrying so much load that the energy, the movement, the kinetic energy that robot has in the motors is enough that it makes sense to take it back, right? So here it's already done. We also see for the industrial robots, the bigger ones, where they move a lot of payload, they already do it today. Mm-hmm. Where we see the discussion is at the moment is with lower and lower payload, the amount of energy you have that is stored in the system is less, right? But this is also where we as TI are trying to show, hey, you don't need to build that. It doesn't have to be expensive. We can do it cheap. We already have an option where we can use one of our power chips to do regenerative energy and store energy locally, to look at the DC link and locally put it down without any processor. This is all possible today. It was not possible 10 years ago, because 10 years ago it was that little energy is not worth the cost that it takes.
Exactly.
This is starting to change now because we have also been looking into it and trying to understand what's the real problem and how can we solve it the cheapest way possible and the smallest way, which is the second. It's not allowed to weigh a lot, right?
Yeah. So this is not an advertorial episode, right? But can you please summarize in 3 sentences what is the whole offer from TI in this field? Thomas?
I mean, we are offering products like processors, sensing parts, ADCs, and we offer the software for the processors. We offer the tools to program the processors. And then in addition, what our systems teams are doing, we are also doing reference designs to showcase the different motor control applications. For single axis motor, we have reference designs. We have reference designs for dual, for up to 6 axis actually, reference designs. And we are also having specific reference designs where we show the capability of the different technologies, like with the gun technology, for example, there is a reference design available. So that really helps the customer to get started and test the performance of the products from TI and how they play together.
Kristen, want to add something in the product range?
Not add, but also to show, right? We were also at CES this year, and here we showed a robotic arm where we showed the joint with the reference design Thomas mentioned, right? With GAN, small form factor, showing EtherCAT communication. We showed a 6-axis design with 6 axes on one processor, very small form factor for the hand to show how to do the control with one processor, 6 motors. And on that demo on top, we also show new technology from TI. We are working on a torque sensor. And this torque sensor is still in sample prototype, so it's very early. We talk about it, but we showed it at CES. And then a second...
And what was the feedback?
The feedback is super interesting technology, very interesting. Customers want to learn more, see how they can use it for different use cases. And this is what we are starting now, this effort. A second technology we also saw is tactile sensing, where we show how to use the Hall sensors with magnets on a material and how sensitive this is. And if you look at that system in the demo, then you see that this has a very nice sensitivity. Of course, there is the problem around you put metal around the magnet. This will distort the fields. But here again, that's where AI comes in, right? The AI can model this out potentially, and then you can have a working system.
Yeah, TI is kind of a one-stop shop, I think, for customers because they get everything
so
what they need.
So I can order a whole robot here now.
No, not a whole robot, but from the electronic side. I mean, from the semiconductor side, you get all the analog components, you get your digital components with MCUs, processors, scaling portfolio here, and you get also on the software side the support here with the SDKs, your real-time operating systems, the AI tools, plus the industrial communication protocols. So that's also available from TI, like EtherCAT and so on, the encoder protocols, and that's all supported in the SDKs actually.
I already asked Christian, do we underestimate, and he didn't answer really the question, Thomas, do we underestimate hardware in the moment from your point of view?
For the industrial robot or for the drives? Or?
For the drives or for the whole robotic system, I would say.
On the electronic side, I think there are still a lot of challenges, like the thermal problem, the efficiency, and also the size. I think those 3 topics are still underestimated, especially for the new cobot type of robots. Customers still have problems to get rid of the heat here. For the more mature industrial heavy load robots, I think they are more working on the cost optimization and that they run 24 hours, 7 days. So with the predictive maintenance now already detecting if there is a problem before the robot fails actually. So that's something what they are working on.
And now you want to answer.
Yes. And okay. So what I would say is I think, yes, it is underestimated. And I think if you look at any company in the world today, you have maybe 10 hardware engineers for the full system, but you have 1,000 software engineers.
Exactly.
And this, at the end of the day, also always brings some, let's say, issues on what do you want to achieve? How much electronics do you want to build in-house? Do I need to buy it externally? And this is also what we see a lot in the companies, that they have to buy externally because they don't have the people to actually do the electronic design. And this is also where we try and help them to make the speed of an electronic design faster by helping with layout reviews, helping with schematic reviews, helping with electronic understanding of discussing with them how does the system work, also how do we think it works, but also how does it really work, because the customer always knows how it really works. We only have assumptions. Our assumptions are typically pretty okay, but sometimes you miss details, and this is where we work with the customers, right? And here, definitely, there is a tendency to, let's say, underestimate the time it takes to do a industrial ready system, because
grade ready.
Exactly,
Yeah.
because there is a difference saying I built an electronic system, I let it run in the lab.
Yeah, that's true.
This is pretty straightforward.
Yeah.
But as soon as you now put it in a industrial environment
with a lot of noise.
Exactly, with all the noise, then suddenly the communication will stop working because the design was not done proper. You didn't do the right termination, you didn't do the right layout in the system, you didn't do the right ground planes in the system to get the return path. All these small details that does the difference. Will it work or will it not work?
Yeah. Yeah.
And this is definitely something we see. I think one good example for this is single twisted pair Ethernet.
Mm-hmm.
What we see, single twisted pair Ethernet for automotive, the way it's done works nicely. As soon as you take that system and put it close to a high voltage noise source with the termination they chose,
But
it's not going to work.
Some experiments on that, right?
Not experiments.
Yeah.
It's already working solutions. We have already test reports showing how do you pass EMC for industrial systems.
Okay.
It's not a thought experiment anymore.
Okay.
It works, and there are already customers doing industrial graded systems with single twisted pair. It's just not done the automotive way because it's not noise immune enough to withstand an industrial environment. And these things are important to grasp and understand. And I think the whole humanoid and cobot with added less weight, single twisted pair Ethernet will definitely be more and more important and will be a requirement to make a low weight robot system and try and minimize the cables. A second thing is the diagnostic discussions that Thomas mentioned. The diagnostic discussions with single twisted pair Ethernet, there is something called an SQI value inside. You can read out of the registers of the PHY, which basically sees what is the signal strength coming from the other PHY during runtime. So you can actually see what is the signal quality at any given time. If this starts to go down, connector, cable, something is going bad. I need to do something before it completely dies. And this is all these things, also small micro steps that are starting to turn the needle more and more in giving options that were not available 10 years ago.
Christian already shared his outlook at the end. So Thomas, at the end, your outlook when it comes to current sensing and the whole robotics field. What do you see, what we will see in the next 1, 2, 3, 5 years?
Yeah, I think the predictive maintenance topic is one thing which will come more.
Really now?
Really now?
Really
yeah.
now.
Especially in combination with AI and all the possibilities here, what you have to get more and more information out of the motor of the system that you can react up front before it really fails, and then you have a problem because your band is standing still. That and also the cost factor, if the system breaks, something can go wrong in your factory. So I think with the predictive maintenance coming more and more, that
Can
problem.
we reduce sensors in the robot?
I think we might have even more sensors in the future because of the safety topic. I mean,
we will have
cobots,
a next episode on safety, right?
Exactly, where we will cover that topic. I mean, TI is offering here radar sensors also on the safety side. I think there should be maybe even more sensors.
But the idea from AI was to reduce sensors, or am I wrong? Because you can...
Yeah, but the use case is getting more and more in the direction that industrial robots or cobots are working next to humanoids. Sure. So I mean the safety standard
next to humanoids or next to human?
Human, sorry, to human.
But this is the next step, Thomas, right?
Yeah,
cobots working next to humanoids. Yeah.
Next to humans. I mean, in the past you had the cage around, you had the industrial robot where it was a place where the robot only worked. But in the future, with the collaboration between humans and robots, I think the safety topic comes, and there you need more sensors. In the past, you just had a fence around it.
Sure. Kristen?
Yeah, on top of this one that Thomas mentioned, right, with the cobots, right, they are already able to work next to humans, but, and there is a but to it, when they are working next to humans, they are working so slow that they are not economical, right? And this is where the mention from Thomas with the more sensors you put around,
you can run faster,
the better you can detect, how
far can we go?
Yeah, let's say, how close is the person allowed to go before I need to slow it down? And I think this is the next step where the efficiency of those robots will increase because of all the sensing. And with AI, you can actually take the data and process it quick enough that you can use it. That was the problem before. And this is where I don't think we will see less sensors. I think we will see more, but the AI will be able to take the data and actually make use of it quick enough because you need to do it real time, right?
But we will talk about safety and sensors in the next episode. Thanks a lot, Christian. Thanks a lot, Thomas. It was a pleasure again.
Thank you, Robert.
Thank you, Robert.
Thank you.